everybody, it's Miss Maneely, and I'm sorry I can't be here today. I have a test that I have to take, so I apologize. But I wanted to go ahead and provide instruction on how to solve various equations excuse me, using the reverse order of operations. A lot of this is going to be review in terms of like using the reverse order of operations and solving and understanding inverse relationships. And so we're going to solve all sorts of equations today. And I'm going to show you how to do it algebraically, and then I'm also going to show you how you can solve, or at least how you can check your answers using the calculator. Okay, let's start with something you know, okay? We're given a linear equation, 3x minus 8, and that equals 10. Think about the steps that you would take to solve for x. What would you do to get x all by itself? Now, when I talk about using the order of operations, if we think about what's happening to x, you know, your order of operations, we start with, you know, we have our PEMDAS, right? Oops, I forgot addition. So we've got our addition. So PEMDAS we know is parentheses, exponents, multiplication, division, addition, and then subtraction finally. And with the multiplication and addition, or I'm sorry, multiplication and division, and then addition and subtraction, we go in the order that they appear in the problem. So if I were thinking about what's happening to x in this original problem, the first thing that we would do is multiply whatever number or whatever value we plug in for x, we'd multiply by 3 first, and then we would subtract 8. And if it's going to be 10, then x has to be a certain value. And in order to figure out what that value is, we want to undo what's happening to x. So the first thing we would do to undo the order of operations would be to move the 8 to the other side. And in order to do that, remember, all of our equations have to stay balanced. So if you want to keep it, you know, keep that line down the middle to separate both sides. To move the 8 to the other side, we know we would simply add it. And that way the negative 8 and the positive 8 cancel on the left-hand side. And on the right, I'm just going to start writing the next line down here because I have more space this way. I'm going to have 3x is equal to 18. And remember, whatever I do to the left, I have to do to the right because the two sides have to remain equivalent. The next thing I would do is undo the 3. So since I'm multiplying x by 3, in order to invert that, I would divide both sides by 3. And so remember, 3 divided by 3 gives us 1, and 1x is simply x. And then 18 divided by 3 gives us a value of 6. And so what we've done is we've used the inverse order of operations, or the reverse order of operations, to solve this equation. And so some of the things you need to remember is that addition and subtraction are inverses of each other. If I have an addition problem, I can undo it with subtraction. Same with multiplication and division. So if I'm multiplying and I want to undo multiplication, I use division. Or we can multiply by the reciprocal, which is the same thing. With exponents, so for example, if I've got x squared, what would undo a power of 2? Well, a root of 2 is going to undo it, because the square root of x squared is simply x. Well, if I have x, say, to the 3rd power, what would undo a power of 3? Well, use a different color. A root of 3 would undo it. The root and the power are going to cancel, and that's going to leave me with x. And if you think about what we did in class last time, so if I have my x to the 3rd and then I'm also taking the cube root, remember this can be written as x. The power is always going to be on the top of the fraction, so we can use a rational exponent. The root is always on the bottom. Whoops, it should be a 3, sorry. The root is always on the bottom. And if I think about what 3 over 3 represents, again, that's just x to the 1st power, or simply x. So the power and the root are going to undo each other. So what about if I have, say, x to the 4/3? So what do you think would undo x to the 4/3? What power could I raise it to? So that's a question mark, so that I'm just going to be left with x. What would undo a power of 4/3? What would you have to multiply 4/3 by? Let me do this down here, 4/3. What would I need to multiply it by to get 1? Well, I'd need to multiply by its reciprocal. And so if I'm dealing with a rational exponent, the way I would undo it is by raising both sides to the reciprocal of my exponent. And those are inverses of each other. And so we're going to be using these relationships to solve all sorts of equations today. There are going to be some exceptions to our rules that we'll have to keep in mind, some things that we're going to have to do that aren't always obvious. And there may be times when the solutions we get actually don't work in the problem, and so we'll have to check all of our solutions. And I recommend doing that with a graph if you can. All right, so using what we just discussed, you're given 3 different equations, and it says for these equations where the variable appears only once. And that's important. If the variable appears more than once, then we have to combine like terms. And if there's no way to combine our variable into one term, then we can't use the reverse order of operations. But if our variable appears only once, then that means that we can get the variable by itself by undoing the operations on x to determine the value of the variable. So what I'd like you to do is pause this video, and I'd like you to take a few minutes, work with the person next to you, and try to solve problems 1, 2, and 3. Once you think you've got the solution, what I'd like you to do is check your answers by graphing both sides of the equation and then looking to see where the 2 graphs intersect. So for example, in number 1, to check your answer, and I do want you to do it algebraically first, we would type in 2x, I believe that's x squared, plus 4, and then on the other side we have the 20. And so what we want to do is graph. So if I do this on a Zoom 6, let's start with a standard window. Okay, I don't actually see the 20, and that's because I need to adjust my window. My y max is only 10, so if I have an equation here where y is equal to 20, I need to make sure my maximum is high enough. So I'm going to go down and make my y max, I'm going to go ahead and just make it 30. And so if I graph, there's the parabola, there's the 2x squared plus 4, and there's the 20. So what I'd like you to do is, with your partner, with the person next to you, I want you to pause the video for about 5 or 6 minutes. I want you to try solving these equations by hand, and then I want you to check your solution using the graph. Okay? So please pause the video now. Okay. If you've done it correctly, in the first one, if you subtract 4 from both sides, you should have 2x squared is equal to 16. Divide both sides by 2, and we get that x squared is equal to 8. So at this point, to get x by itself, remember, if I'm raising x to a power of 2, to undo it, I want to take the square root of both sides. And so that leaves me with x equals the square root of 8. And so one of the things we do have to remember, if you can think back to our quadratic unit, when you take the square root of both sides, remember there are 2 possible roots to 8. There's a positive root and a negative root. And to figure out the square root of 8, we can either reduce our radical, and if you think 8 is equivalent to 4 times 2, and 4 is a perfect square, so if I rewrite 8 as the square root of 4 times the square root of 2, I can take the square root of 4, and that gives me 2 times the square root of 2. And again, there's going to be 2 roots. Or you can simply take the square root of 8 on your calculator and get the decimal equivalent. So another way of writing that would be to do plus or minus 2.828. Now if we go back to our graph, remember this is what we already had set up, I can use my second calc menu and find the intersections. Now because there are 2 points of intersection, you'll need to move your cursor close to one of the points, and that should give you the negative root. So that's going to be the negative 2.828, and then we'd have to do the whole process again to find the other root, which is a positive 2.828. All right, and number 2, in order to solve for x, remember we're using the reverse order of operations, so since the last thing I would typically do is addition and subtraction, in a problem like this, the first thing I want to do is take care of the addition and subtraction. So instead of the minus 8, I'm going to go ahead and add 8 to both sides, and that gives me 4 times the square root of x, and that is equal to 4. To continue solving, I'm going to want to divide both sides by 4, because that would become next, and then I'm left with the square root of x is equal to 1. And how do I undo a square root? Well, I raise everything to the power of 2. And so that leaves me with x equals 1 squared, or simply x equals 1. And if I graph this on my calculator, if I have 4 times the square root of x minus 8, and then in my second equation I have negative 4. I'm going to go back to doing this on a Zoom 6 window. I can see that there's only 1 point of intersection. So if I go to my calc screen and choose intersect, I can see that x equals 1 when y is equal to -4. Okay. Oops, one more. So we've got 5x to the 2/5 is equal to, is that, actually I think that's a 3/5, isn't it? So we have 5x to the 3/5 minus 2 is equal to 38. Again, I'm going to undo my subtraction first. By adding 2 to both sides, I get 5x to the 3/5 is equal to 40. We'll divide both sides by 5, and we get x to the 3/5 is equal to 8. And then again, to undo the power of 3/5, I'm going to want to raise both sides to the reciprocal of that, which would be 5/3. And so I'm going to end up with x is equal to, remember when we have a number raised to a rational exponent, we want to deal with the root first. Since the root is the 3, I know the cube root of 8 is 2. And then I'm left with 2 to the 5th power, which is 32. And if you're not comfortable doing that in your head, we can just basically take 8 and raise it to the power of 5/3. But you do need to make sure you put that in parentheses. With a newer calculator, it pushes it up into the exponent, so the parentheses aren't necessary, but it is a good habit to get into. Okay, and if I graph this on my calculator, then I know I'm going to have 5x raised to the 3/5 minus 2. And then I have another equation at 38. Now, I know right now that since I have a y value of 38, I need to adjust my window so that it goes at least to 38. I'm going to make it go to 45. Okay. So when I look at my graph, I can see that the graphs don't intersect yet, but I can see that they look like they will intersect if I could just move the screen a little bit further to the right. So moving it to the right means that I need to increase my x max. Well, if I look at my solution and I know that my solution means that x has to be 32, then I know my x max has to be more than 32. So let me go ahead and make it 40, because we're just checking here. You might have to do some trial and error if you're using the graph to solve. But now that I see the intersection, if I hit second trace, intersect, I can see again that it confirms that my x value is 32. Okay, so I'd like you to take a look at the next 3 problems. They're very, very similar to the ones you just did, but this time it's going to be really, really important for you to check your solutions with a graph. And that's because this is where we're going to run into some challenges. So again, I'd like you to pause the video. And then I'd like you to work with a partner, solve the 3 equations, make sure you check the solutions with a graph, and then I want you to pay attention to the special cases that are identified below. It says when the original equation involves an even power, we must remember to do something. When the original equation involves an even root, we must remember to do something else. And so I want to see if you guys can figure out what goes in those blanks before I tell you. So again, I'd like you to go ahead and pause the video and work out these 3 problems. Okay, so if you did everything correctly, in number 4, when you divide both sides by 2, you should get that x to the 2/3 is equal to 4. And then to undo the 2/3 power, we're going to raise both sides to the 3/2. Okay, and so I'm going to end up with x is equal to, well, the square root of 4 is 2, and if I raise that to the 3rd power, I get 8. So that's what we would get algebraically. If I look at my graph and plug that in, we have 2x to the 2/3. Actually, I probably should put parentheses around that to make sure that you guys are doing that. So I'm going to go insert, oops. There we go. And then the second equation is 8. And again, I'll do this on a Zoom 6 window. Okay, so look at the graph of 2x to the 2/3. It's not one of the functions that we've seen before. It sort of looks like an absolute value, but it's not a perfect v. That's actually a curve. I also want you to notice that there's actually 2 points of intersection. Now, It's not as obvious in the form of the equation the way it's written on your paper. But remember how we said that if we've got x squared is equal to 16 and I take the square root of both sides, I've got to remember to do plus or minus the square root of 16 or plus or minus 4. Well, if you look at this problem, the original problem involves an even power. So even though it's written in a different format because the exponent is a fraction, because the number on top is even, that tells you that it's an even power. And anytime we're dealing with an even power, we have to remember that there are going to be two roots. So we've got to remember the plus or minus. There are two roots. Even if they're imaginary, there's going to be two roots. Okay, and so one of the things you want to do on your paper, if you're given a list of equations to solve, you want to go through and circle all of the ones that have an even power. And remember, if we've got x to the m over n, the number on top is the power, the number on the bottom is the root. So if the number on top is even, you've got to remember to do a plus or minus. So on your paper, you're going to want to go through and circle all of the even powered problems and maybe put a little plus or minus next to the problem so you don't forget that. Let's take a look at number 5. So we've got 3 times the square root of x plus 5 is equal to 2. We're going to subtract 5 from both sides, and that gives us 3 times the square root of x is equal to negative 3. If I divide both sides by 3, we get that the square root of x is equal to negative 1. And then to undo the square root of x, I'm going to square both sides, and I get that x is equal to 1. All right, well, let's see what happens when I graph it. So we've got 3 times the square root of x plus 5. And in the second equation, I've got a 2. And let's go ahead and graph it and see what happens. I've got a square root function, and I've got a horizontal line that don't intersect. If they don't intersect, that means that there is no real solution. And so even though algebraically I came up with a 1, I can see from the graph that there really is no intersection point. This is what we call an extraneous solution. So algebraically, we have done nothing wrong here. We've done all of the math correctly. We've used correct algebra, and we came up with a value for x that actually doesn't satisfy the equation. Think about what would happen if I plug 1 in for x. I'd have 3 times the square root of 1 plus 5. Well, 3 times the square root of 1, the square root of 1 is just 1, and 3 plus 5 is 8, and that is certainly not equal to 2. And so anytime we're dealing with a square root or an even root function for that matter, we must check our solution. Because it is possible that we can do all of the math correctly and still end up with a number that doesn't satisfy the equation. In fact, if we take a look at this step right here, where we had the square root of x is equal to negative 1, that is a point right there that you should be able to tell that this is not going to work. Is it possible to take the square root of a number and get a negative? No. So that would be an indication that we've got an extraneous solution. All right, let's take a look at number 6. In number 6, we've got x to the 3 halves plus 1. And that is equal to negative 7. So if I have x to the 3 halves, if I subtract 1 from both sides, I'm going to do this up here, I'm going to have x to the 3 halves is now equal to negative 8. And if I raise both sides to the 2/3, because remember, if my original exponent is 3 halves, to undo it, I'm going to raise it to the reciprocal. That leaves me with x is equal to, well, the cube root of negative 8 is going to be negative 2, and if I square that, I'm going to get positive 2, or positive 4. And I can do this on my calculator if I go to my home screen. Now, it's important, you want to make sure that you put the negative 8 in parentheses, and then raise it to the 2/3 power. And we get 4. Let's see what happens when we graph it, though. Okay, so if I have x to the 3 halves plus 1, and then in my second equation, I have negative 7. Again, this is still the Zoom 6 window. And what do you notice? The two graphs don't intersect. So this is another example of an extraneous solution. And so what we'd have to say when you get to this point is you'd actually just cross it out. And then you just say no solution. And sometimes we end up with two values for x, and so you have to check both of them. And then it may be possible that one of the values works and the others don't. So this again is going to be no solution. Okay, and so if we think about what that original problem was, we had x to the 3/2. Well, remember, when you have a rational exponent, the number on top is your power, and in this case it was odd, so I don't have to worry about anything when I've got odd exponents. But the number on the bottom was even, so that's another example of an even root. It's not always going to look like a square root or a fourth root. Sometimes it's going to look like a fractional exponent with an even number in the denominator. So whenever you have an even power, you want to remember to include a plus or minus. Whenever you have an even root, you want to make sure you check the solution. If you have an odd power or a root, you don't have to worry about a thing because the sign of those numbers isn't going to cause you any problems. Okay, so again, we can only use the reverse order of operations when it's possible to arrange the equation so that there's only one expression involving x. So the next question says, which of the following cannot be solved by reversing the order of operations? Because the idea is to isolate the term involving x. That's our first step. Isolate the term involving x. Okay, and we're going to undo addition and subtraction first. And then we'll undo multiplication and division. Okay, and then after that, use inverse operations, and usually at this point it's dealing with exponents and roots. Okay, and then the last thing you want to remember, if you start off with an even power, use a plus or minus. So if we're dealing with an even power, use the plus or minus. If we're dealing with an even root, check your solutions. Okay, and sometimes just using the graph is the easiest thing to do. So again, let's take a look at these 6 examples. In letter A, think about it. Is it possible to get x all by itself? Is there any way that I can combine the x squared term with the 4x to get one term involving x? And the answer is no. So I would not be able to isolate x and then undo the operations that are happening to it. So I would not be able to use the reverse order of operations here. So I would not be able to reverse PEMDAS in letter A. Let's take a look at letter B. Is it possible to get the expression involving x by itself? Because right now I have, it looks like the cube root of x minus 1 plus 4 is equal to 12. So because it's possible to get that expression by itself, right, I'd subtract the 4, and then because I'm dealing with a cube root, I could cube both sides, and that would give me x minus 1 by itself, and then I could add 1 to isolate x. So B is possible to use the reverse order of operations. Okay, so take a look at the next 3. Which ones can you use the reverse order of operations and which one can't you? So take a look at letter C. I've got 2 expressions that involve x. There's no way that I can combine them together into one. And so this is an equation that I cannot solve using the reverse order of operations. If you gave me an equation like that, I would graph both sides and use my calculator with a graph to figure out the points of intersection. I wouldn't even bother trying to do that algebraically. In letter D, I have 1 expression involving x. That means I can add 3 and divide, actually I can't divide by 5, I'm sorry. I would add 3 to both sides, and then I'd have to think, if I have x in my exponent, what could I do to get it out? And this would be an example of using logs to solve. So I'd have to take the log of both sides. We did that first semester, so it might be a little while. In letter E, I have 1 expression involving x. It's an absolute value, but it's possible to get it by itself. And in letter F, so this is a yes, This is a yes. In letter F, I've got two expressions involving x. I cannot combine them because the exponents are not the same. If it was x squared plus 3x squared, I could combine them and I'd have 4x squared and I'd be able to get it by itself. But I can't because the exponents are different. So this is not an example where I could use the reverse order of operations. Okay, on the back, you have several different practice problems. Again, what I recommend that you do is go through each problem, look to see first if you have an even power, because anything with an even power, I want you to write a plus or minus next to that problem. And then go through and look at the problems with roots or fractional exponents. Look at the denominator of the fraction. How many of them have an even root? And if they have an even root, I want you to write the word check or place a check mark next to the problem so you remember to check your solution. Okay? I'd like you to work with the person next to you and complete these exercises. At the end of the period, I'd like you to push play and I will have the answers posted for you. So please go ahead and press pause now. Okay, so here are the answers to the practice problems. If you need to pause the video for a second and take a look at the work that I've done here. In number 7, you're dealing with an odd root, so you don't have to worry about the plus or minus or checking your solution. But in number 8, that's an even root, so you must check. And in this case, it does work. In number 9, again, we're dealing with another even root, so you have to check. And notice that when we get to this line right here, we have the square root of something equals something negative. Right then and there, you should know something's not right. It's not going to work. But even if you get through the whole problem, when you check your answer, you'll find that it does not work. And so you need to make sure that you say that there's no solution. Number 10, even though you don't see the square root symbol, because the original function is raised to the 3/2 power, that half, remember, is another even root, so you have to check. And in this case, it does work. In number 11, you're dealing with a power of 4/3, or an exponent of 4/3. That means you're dealing with an even power. You have to remember the plus or minus. The plus or minus comes in here when you're undoing that power. And so notice I'm going to end up with x plus 1 is equal to positive or negative 27. You're not going to wait till the very end and put the plus or minus. You're going to put the plus or minus when you're taking the root, and that occurs at that step. And so at this point, we want to split the problem into two parts. That means that x plus 1 could be a positive 27, which is this solution, or x plus 1 could correspond to a negative 27, which is going to be the other solution. And so you're going to get two completely different answers in this case. Another way to check to make sure you've done it correctly is to graph both sides of the equation and see where the two graphs intersect. 12 and 13, we have equations that involve two terms with an x that we can't put together. So the best course of action here is just to graph both sides of the equation and solve. So pay attention to how I've written the equations in my calculator. And then notice in both cases there is only one point of intersection. So when you're using the graph, you don't have to worry about remembering a plus or minus or remembering to check, because your graph is going to show you all of the possible solutions. You just look to see how many points of intersection there are and then make sure that you calculate or determine those points. The last problem is a word problem. It has to do with an amusement park. It's one of those where the wall circulates and you get sucked up against the wall. You're given that the rotor moves at 8 meters per second, and so that's the speed, and that's your value for S. When you plug 8 into the equation, you're going to solve for R. Now notice that I waited when I had my fraction 8 divided by 4.95. I didn't do the calculation at that point because if you do, you're going to get a decimal value, and we want to wait till the very last possible minute to do our rounding. So I only want to round one time. So if it's possible to wait until the end, I notice that I left the fraction as is and then I squared it. And so on my calculator, you can see on the left, I just did it as one expression, one entry, instead of doing it several times. So if I want to check to make sure that's correct, basically what I want to do is take 4.95, this is the original equation, 4.95 times the square root of R. Well, R is just the value I got from my previous answer. And notice that the negative sign above it has the word answer to it. So if I type in second answer, my calculator will recall the entire number. So I'm not rounding and putting in 2.61. The calculator remembers all of the decimal values. And so when I press enter, you can see that I get the 8 back. So you do have to be careful if you end up rounding an answer. if you try to plug a rounded answer back into the equation to check to make sure that you've done it correctly, then it's going to be a little bit off. So just keep that in mind. It's called a rounding error. And again, the reason that we checked this problem is because we were dealing with an even root. And so we have to make sure to do the check. All right, I hope that helps. You can go ahead and begin your homework assignment, and we will go over it next class.